Okay then, last bit for today. I want to talk a little bit about isomerism. We often find that a molecular formula is not enough to specify which organic molecule we're talking about because more than one molecule can have the same formula. So for example, if we said that the formula for some molecule was C3H6O, right, and we might have done this by those mass percentage data to work out an empirical formula that we did this stuff back in the first week of lectures, yeah? We might work out that that's the formula, then that's not going to completely tell us what the molecule is, because the molecule could be this one. This is a molecule that has that formula. This would be propanone, a ketone. There really must be a handout for all those suffixes. I'll go find that for you. Sorry. So for a ketone, the suffix pit at the end of the word is -one, O-N-E, not one, but -one. And so that would be the name of that molecule, which has a formula C3H6O. But we could also write a molecule like this, which also has the formula C3H6O. And that one would be propanal, which is an aldehyde. And so these are quite different molecules. They're going to have different, well, they're going to smell different for a start, but they're going to have quite different chemical properties. And so we need to be able to know which one we're talking about. Yeah? And so just giving the molecular formula in this case isn't going to be enough. So if we have two molecules which have the same molecular formula, but they have different structures, we call these isomers. And for those two molecules that we just looked at, the propanone and the propanal, they are what we would call functional group isomers, because the difference between them is that they have a different functional group, right? So that's quite a significant difference between those two isomers. One's a ketone, one's an aldehyde. So they're called functional group isomers. And those are important, but they tend to be not things we dwell a lot on because they're not very interesting. They're just different molecules. What we tend to get much more excited about are the ones where the differences between the molecules are much more subtle. Okay, so what I want to do now is I want to look at three types of isomers, relatively quickly, hopefully, where the difference between the two types of molecule is much more subtle. And they're going to get increasingly subtle and, dare I say it, increasingly more important. So, first of all, here's an example. If we have a formula C3H8O, then we could write a molecule that looks like this that would have that formula. This is an alcohol, right? And specifically this one, where the OH is on that end carbon, would be called, oh now look, oh, aren't we being good? You could just call this propanol, because it's on the end, so remember if it's on the end we don't have to specify. Or you, if you wanted, you could call that propan-1-ol. Now this is actually different to that previous slide, isn't it? But this is actually what is taught at school now, yeah? With the number in the middle? Where are my nomenclature freaks up the back? Yeah? It used to be that you could either call that 1-propanol, where the 1 was out the front, or propan-1-ol, where the 1, it comes right before the part of the name that tells that the 1's referring to, right? So the 1's telling you where the OH group is, where the alcohol functional group is, and so you can name it like this with the 1 right in front of the part of the name that talks about it being an alcohol. This is probably the preferred way, to be fair, rather than having the number out the front, if you're naming the position of the functional group. So that's one way you could draw that molecule, but of course the other way is if you put that OH on the middle carbon rather than on the end carbon. And so now you have a molecule that we would call propan-2-ol. And so these two are isomers of each other. They've got the same formula. Now they're both the same sort of molecule. They're the same class of molecule because they're both alcohols, but they're still different to each other based on the placement of the functional group within that carbon framework. And what you find, and we've kind of talked about this already a little bit with this molecule here, is that even just simple alkanes, just the class of molecules where you only have carbons and hydrogens and only single bonds, you can get isomers with them. And so, for example, a molecule which has the formula C4H10 could have either of these two structures, one where the 4 carbons are all in a chain, another where you have 3 carbons in a chain and the 4th one hanging off the side. Right. Again, isomers. And I think here I've got this business about, yeah. So there's a little mathy thing that you can do to work out how many possible isomers you can have. It's so I can't remember the mathy name for it now. Doesn't matter. Calculations show that if you have C10H22, then that has 75 possible isomers. Right? So there's an easy exam question just there, or it's an easy exam paper. Draw all the isomers for C10H22. If you have C40H82, now 40 is getting up there, but in a sort of a biological context, 40 carbons is nothing. I mean, you know, in proteins you have a few hundred carbon atoms. This has 6.25 times 10 to the 13 isomers, right? Which is a lot. Okay. The most interesting isomers are those in which the connectivity of the two molecules is the same. So in other words, all the same bits are attached to all the same other bits. In those two molecules, the OHs were attached to different carbons. But you can get isomers where everything's attached to the same other pieces as the other isomer, and yet the molecules are still different. These sorts of molecules are only different in the way that the different parts of them are arranged with respect to each other in three-dimensional space. Right? So they're not different in terms of how they're put together, how their different parts are connected to each other. They're only different in the way that certain parts of the molecule are related to other parts of the molecule in 3 dimensions. And so for this reason we call them stereoisomers. Stereo referring to the original idea of stereo, which is coming from 2 different places. So sound in 3 dimensions, yeah? And this, is this a high school word? I'm not sure it is necessarily now. So this might be new. Just the word anyway. And so we're going to see there's 2 different types of stereoisomers, one which you've seen, well actually both which you may have seen, but one of which is very important for going on into later in the year. So, one class of molecules in which we observe this stereoisomerism, if you like, are in alkenes, compounds which have carbon-carbon double bonds. And so here's an alkene up here. This one would be called F-ene. For an alkene, that middle part of the name, instead of being A-N, becomes E-N. So F for 2 carbons, ene, with an E on the end. Right? And the thing that you need to appreciate about this is that this carbon-carbon double bond makes the whole molecule rigid. If you're just a carbon-carbon single bond, like say in here, then that single bond can kind of act like an axle. And so this end of the molecule can spin around with respect to the other end of the molecule. Right? So single bonds are like axles. If you have a double bond, that's kind of like trying to put 2 axles between a pair of wheels on your car. And if you think about it, that's not going to work. Right? The wheels won't turn. One wheel won't turn freely if you're holding the other one if you've got 2 axles joining them. And so a double bond makes this molecule rigid. And so you don't get what's called in the game free rotation. And so what that means is that these 2 molecules are different to each other. Right? So here we have, this would be 1,2-dibromoethene. Yeah? And both of these molecules would be 1,2-dibromoethene because they both have a bromine attached to carbon number 1 and a bromine attached to carbon number 2, and each of those carbons also has a hydrogen attached to it and is double bonded to a carbon. So these two molecules have the same connectivity. All the same stuff is attached to all the same other stuff in these two molecules, but they're still different because you don't have this free rotation about this bond in the middle here. So these two bromines are always next door to each other. These two bromines are always on opposite sides to each other, right? So they're different molecules. They're isomers. But because that difference is only about how the bits of the molecules are arranged in 3 dimensions, these are examples of stereoisomers. Now we need to have a way of distinguishing one from the other, and so we have extra little bits of name that go on the front. The one where the two bromines are on the same side of the carbons as each other is called cis, and the one where they're on opposite sides of the carbons to each other is called trans. So trans is like a cross. And so we have extra bits of name to distinguish one of these stereoisomers from the other. And it turns out that these molecules are actually quite different. They will have quite different chemical properties. Different melting points, different boiling points, different smells, different colours potentially, quite different molecules. Okay? So this type of isomerism you get with alkenes. So you get cis and trans isomers with alkenes. Pretty much only with alkenes. And then the third type is the most interesting and probably the most important, and the one we're going to spend most time on later in the semester. And this is the type of stereoisomerism that you find when you have a carbon atom in a molecule which is attached to 4 different things. So you have a tetrahedral carbon, and the 4 things that are attached to it are all different to each other. And so there's a little picture, and those 4 coloured balls just are to represent 4 different things. And if you're sitting there going, well, this seems a bit weird, in fact, this molecule that we started off with, this would be an example of one of these, right? Because this carbon here has got a methyl group attached to it, a CH3, it's got an H, which we haven't drawn in, it's got a CH2-CH3 group, and it's got a CH2-CH2-CH3 group, right? So even though this has got 3 carbons attached, it's not just the carbon, it's the thing as a whole that's attached to it. So this carbon here would be one of these carbons that has 4 different things attached to it, right? And that's quite a simple little molecule. So here's a wee diagram of this, and what we're going to do is we think about its mirror image. Right, so this little thing here is supposed to represent a mirror. I think I learned that in 6th form physics somewhere. And then here's its mirror image. And the point of these sorts of molecules is that if you make its mirror image, then its mirror image is a different molecule to the one that you started with. And oftentimes, it's very hard to see this because you have to be quite good at doing things in 3 dimensions in your head. Not everybody's wired for doing that. So what we might try and do is get some little plastic models over in the lab so you can see how this works. Right? It's pretty obvious once you see it and you go, oh, okay, that makes sense. But sometimes you have to see it in 3 dimensions to get it. So we have this molecule and the other one, its mirror image. These are stereoisomers of each other because they have the same formula and everything's attached to all the same other things, yet they are still different to each other. And I believe the word that's used for this at school is called optical isomers. Here we give it an even fancier name, we call them enantiomers. Right? So this big red word down here is a special name that's given to pairs of isomers which are mirror images of each other, but still different molecules. And of course, the reason why this is very important in the sorts of things you're going to be seeing later in the semester, or the biological sort of chemistry, is that these molecules involve a carbon atom that's got 4 different things attached to it. Do we know what these are? This is an amino acid, right? One of the fundamental building blocks of all the molecules in your body. All of these have the possibility of being one way or the mirror image, right? Turns out that all of the amino acids in your body are all the same one. You don't have a mixture, they're only one. For reasons which I'm not sure anybody actually has really quite nutted out yet, but nonetheless, that's the way it is. We call the carbon atom to which the 4 different things are attached a chiral carbon. And so we often call molecules which contain chiral carbon atoms chiral molecules. Oh, and there you go. For example, alanine. And so part of the game with this is being able to look at a molecule that we might give you, and it might be a picture like that one up there, and get you to identify any chiral carbons that might be in there. And so what you need to be able to do is to look and find a carbon that's got 4 different things attached to it. And once you've done that, then of course, oh, where are we going here? Right. You need to have some way of distinguishing one from the other, like we do with cis and trans with those alkenes. And there is a system to do that, but you don't do that at school, and we're not going to do it here. Yeah?
I think I must have missed something. Why can you not just flip it around?
Because it doesn't work. If you flip it round, you don't... See, remember this is in 3 dimensions. If you take that and you flip it round, so the H is here and the NH2 is there, the CH3 here sticking out towards you, when you flip it round, it's going to be pointing away. But in this molecule, it's pointing towards you. You see, so it's different. It's like I say, if you have these little models, then you go, oh, obviously. But yeah, it can sometimes be a bit hard to see. Yeah. No. Because if this molecule has this pointing towards you and that one pointing away, and the other one effectively has those 2 flipped around, those will be different molecules. They'll have different properties. Well, actually, that's not completely true. What it says here is that, in fact, they have very similar properties, but they are still different under certain circumstances. Right? And so the example, ignore all this, blah, 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 feet and shoes, doesn't matter. This, right? This is a sort of classic thing that they tell you about at school. If you can have these 2 molecules of which are enantiomers, sorry to use the big word, of each other. So here's a molecule here, it's got a ring of carbons at the top there, and then some stuff hanging off the bottom, and this carbon here is a chiral carbon, right? Because it's got an H attached to it, it's got this thing attached to it, it's got a CH2, which in turn is attached to a CH2 over this side, and it's got a CH2 attached to a CH, which is part of an alkene off that side, right? So those differences are quite subtle between those 2, but nonetheless, this carbon has 4 different things attached to it. One of the enantiomers of this smells like oranges, the other enantiomer smells like lemons. And so this is the thing. These 2 molecules, the 2 enantiomers of this, will have the same melting points and the same boiling points and probably the same... Actually, no, I won't say the same colours, because even that can sometimes change. But the way that they interact with other chiral molecules is different. And in the context of smell, when you smell something, the molecules go up into your nose, or in fact, actually a lot of the time up into your mouth, which is why you can't smell properly when you have a cold and your nose is blocked. No, sorry, no, it's the other way. It's this taste one. Forget what I just said. When you smell something, the molecules go up into your nose, and there's little receptor things in there to which these molecules attach, right? And it's like feet and shoes. So imagine if your feet are chiral objects, right? One foot's the mirror image of the other, but they're not the same. And you know that if you get up in the morning half awake and try and put your left shoe on your right foot. It doesn't work the same as if you put your left shoe on your left foot. Yeah? Because your feet are chiral objects and your shoes are chiral objects as well. They're mirror images of each other, but they're not the same. Unlike socks. Socks don't care. Socks are not chiral objects. So it doesn't matter which sock you put on which foot. It still works. But it does matter with shoes, right? You have to have the correct match of one chiral object, your left foot, with another chiral object, your left shoe, for there to be a good interaction. And this is the same way that smell works. The little smell molecules are chiral, the little receptors into which they fit inside your nose are chiral as well, and you have to have the correct fit for the molecule to smell a certain way. Different enantiomer, doesn't fit into one receptor, has to fit into another receptor, which then sends a signal to your brain and says oranges rather than lemons. Yeah? Horribly interesting stuff.